Okay, we're going to talk about multiplication now. So the modular arithmetic via tables part 2. So you'll notice that I have the chart up on the top right of the screen. This is the multiplication chart. And so you can see I'm using an asterisk in this case. Same thing as before. I have the numbers 0 through 11 in the top column and leftmost row. Top row, leftmost column, sorry. And then all of the values inside based on multiplying those numbers together. Like 5 times 7 would be 35, but 35 divided by 12 is 2, remainder 11. So we get an 11 there. So basically we're filling this all in. You'll notice that the symmetry is not the same for this particular table as it was for the arithmetic. It doesn't mean that there isn't symmetry here. In fact, there is some. It's just a little bit more complicated, arguably. It's not, not terribly complicated, but it's definitely more so than what we saw in the table for addition. But let's take a look at some questions here. So the first question is, does the congruence class of 3 have a multiplicative inverse? So what do we mean by multiplicative inverse? Well, when we think about that, an additive inverse, as we mentioned, is a number that it adds to its inverse, and the sum of that is the additive identity, which is 0, which we get because 0 plus anything is itself. So in the case of multiplicative inverses, we're looking for something multiplied by a number that will return the multiplicative identity. And that's the number that when you multiply by it, it doesn't change the value, which I think we all know that that's the number 1. So what we're really asking in this first question is, is the answer to the question 3 times x congruence to 1 mod 12. And what's x? That's what we're really looking for. What can I multiply by 3 and I get 1? So just like we did with the addition table, I'm going to come over here to 3, and I'm going to go across here until I find the number 1. And it doesn't look like I have one. So yeah, so what this is basically saying is that no matter what I multiply 3 by, in mod 12 there will never be a 1. So this one does not have a multiplicative inverse. So no inverse. Not all of them do. Not all sets of numbers do. A good example is the integers. Integers and I mean this is obviously a subset of the integers, but think of it like this. If I have the number 3, again, the multiplicative inverse of 3 would be 1/3, but 1/3 is not an integer. So not all sets have multiplicative inverses. So this one isn't really any different in that sense. Well, we said the 3 doesn't have one, but what about 5? Let's take a look at that. So same thing, I'm going to come over here to 5, I'm going to come across here, and I do have one. So what I can think of here is that this is the question then. I'm gonna leave the bars off for now. We know what that means. 5x congruent to 1 mod 12. That's what we're trying to do. We saw that that happens right here. So I know that a inverse of 5 exists in mod 12. And all I have to do is go up to the top here and see that it's 5 itself. So what we're saying is that 5 is its own inverse in this case, in mod 12. And let's just check. So 5 times 5 is 25, and divide that by 12, I get 2, with a remainder of 1. So it turns out that 5 is its own inverse in mod 12. It's kind of interesting. Definitely different than other stuff we've looked at before. Okay. Last question. And this one is a throwback. This goes back to even Algebra 1 you learned about this. You may remember something referred to often as the zero product property. In other words, if we multiply 2 or more things together and the product is 0, then we know that at least one of those has to be 0 for that to work. So basically what we're looking for is in mod 12, if I have the product of 2 things and I know that the product is 0, then can I say the same thing, that one of those must be 0? Well, if I go back to my chart again, I notice that in the top row, inside the chart, 0 times anything is 0. So there's an example where 0 clearly is one of the options. And if I look at this column, clearly anything times 0 is also 0. So far, so good. But the problem is, if I look at row 4 here and I start coming across, all of a sudden I notice if I get 4 times 3, I have another 0. And that makes sense because 4 times 3 is 12. 12 divided by 12 has a remainder of 0. Same thing happens at 6. Same thing happens at 9. So it turns out the zero product property is broken in modular arithmetic. We cannot assume that when we're multiplying two numbers together, that one of them is going to be equal to 0. At least not in all cases. So the answer to this one is no, we cannot conclude. Now, the natural question might be next, what can we conclude? And are there some things that we can generalize? And I'm going to leave that up to you. So think about that. Okay?